Right, we'll have a look at the properties of amines as bases now. Let's hope we don't get attacked by a hamster or anything like that. So we'll draw an amine. Remember the name of this one? Phenylamine. It's the phenyl group. It's obviously the amine group there. Don't forget the lone pair of electrons on that nitrogen there. That's very key in this topic. Now, phenylamine can react with hydrochloric acid, and we know that hydrochloric acid is made up of H plus ions and Cl minus ions. Obviously, it's going to be the lone pair of electrons on here, which is going to be attracted to that H plus ions there. So I've taken electrons away from this nitrogen here, added to an H+, therefore that nitrogen there has now got a positive charge, leaving the Cl- here. The Cl- is a spectator ion. So we'll call this phenylamine. We'll call this structure here phenyl ammonium chloride. So if we can compare this reaction, actually, can't we, to ammonia plus HCl. You would have done this at GCSE. Ammonia plus HCl, ammonia plus hydrochloric acid, makes ammonium chloride. So that's ammonium chloride. This is just phenyl ammonium chloride. So it's ammonium chloride, but with one of the H's with a phenyl group on it. So there's nothing complicated about that name there. All we've done is we've just replaced one of those H's with a phenyl group there. So it's just basically, it's a base and an acid making a salt. Here we've got a base and an acid making a salt. Base, acid, and that makes a salt. Okay. So let's do another one. So if we had ethylamine, and hydrochloric acid, that would make ethyl ammonium chloride. Sorry, that's the word equation. I can do the symbol one as well if we like. And the ethyl ammonium chloride here, like that. Now, this is an ionic substance. This here is an ionic substance. However, our start materials are not ionic. This is just covalent. It's a simple covalent structure, this. Simple covalent. And this is simple covalent. So HCl is a solution. So basically we'll put a simple covalent structure into a solution. We're getting an ionic compound. Simple covalent structure into the solution and getting an ionic compound. Okay? So it's soluble. So these are soluble. Ionic compounds are soluble. So they're soluble ionic salts. What we can do is we could evaporate the water from this here. If we evaporate the water and we could crystallize it, and we could get crystals of phenyl ammonium chloride. Okay, so we can crystallize that by removing the water, evaporating the water. Because it's ionic, it'll be a solid. Again, if you want to get crystals of ethyl ammonium chloride, then we would just evaporate the water off this and we'd crystallize that as well. And we'll get a solid produced. Okay, so let's imagine we have made our phenyl ammonium chloride here. Let's just draw that out again. And I wanted to get back my original phenylamine, so I wanted to kind of reverse this reaction here. What I would do is I would react this with a base. So we've got our phenyl ammonium chloride here, and I can react that with a base. So OH minus. And what that base would do is, like any base, it would remove a proton from here. So a proton is an H plus to make water. So let's imagine we've removed this H plus here. That would make water. And again, the Cl minus is just a spectator ion. And then we'll get back to our phenylamine. So we've got our phenyl ammonium chloride here, and phenylamine is a product. Whereas over here, we had phenylamine as our reactant, and phenyl ammonium chloride as our product. Okay? So a strong base, something like sodium hydroxide. We'd remove the proton from the salt and regenerate the amine. Okay. Now, what we find is, that because this is an ionic substance, that's soluble. And because this is a covalent substance, it's insoluble. So if we were to do this experiment, now we know from last lesson that amines have got this very, very horrible smell. So before I add an acid, I'd smell that horrible smell, that rotten fish smell. I'd add some acid, and then that smell would go away. And the reason why that smell would go away is because the product is soluble, so it'll be dissolved in the water, so I wouldn't be able to smell it. Then, if I added a little bit of sodium hydroxide, I would make my original reactant back again, which is my original amine, which is insoluble, and I will be able to smell it again. So if I started off with an amine, added an acid, the smell would go away, and then if I added a base to that, the smell would come back. So just a little observation there, if you were to do that particular thing. So we're now going to look at base strength of amines. We know the bases because a base accepts protons, and that's what's going to happen here, because we've got a lone pair there and it's accepting a proton, so it's acting as a base. We're going to look at the strength of these bases. We're going to change the structure of the amine to look at the strength of amines as bases. So there we've got ammonia, and that can act as a base because that lone pair of electrons can react with an H+. So they'll more readily those lone pair of electrons can be donated gives an indication of the strength of the base. If I change one of those H's to an R group, so we've now got a primary amine. What that does is that R group, because it's a bigger group than that hydrogen there, it's got more electrons in it. And what happens is some of those electrons are pushed onto the nitrogen, and you represent that push of electrons by a little arrow like that, and it's showing that those electrons are being pushed towards that nitrogen there. And we'll call that the inductive effect. And because electrons are pushed on that nitrogen there, that makes that nitrogen a better electron pair donor. So that pair of electrons there is better donated than that pair there. So it's more likely to donate to an H plus compared to just ammonia by itself. So if we put another R group on it, we make a secondary amine, then you've got a greater inductive effect. Therefore, that lone pair of electrons is even more likely to be donated to an H plus. And likewise, if we go to a tertiary amine, where all of these H's are R groups, then you've got quite a significant inductive effect, and that lone pair of electrons is very easily donated to an H plus. If, however, you've got a phenylamine, remember benzene ring? Here we've got an electron charge cloud which is spread over the molecule here. We just put on an amine group. What happens is we don't just get delocalization of those electrons in those 6 carbons there, you actually get delocalization of those electrons in those 6 carbons there and that lone pair. So you get delocalization around those 6 carbons and that lone pair here as well. Now, that means that this lone pair of electrons here is not as readily as available as those lone pairs here, because it's now part of this delocalization system, which makes it very stable. So that lone pair of electrons is very unlikely to react with an H plus ion. So we've got 5 different structures here. We've got ammonia, a primary amine, a secondary amine, a tertiary amine, and a phenylamine. So this one is the weakest base. This one will be the strongest base. However, I'm going to come back to that one in a second. Actually, this one is the strongest base. This one is quite strong. And this one, it's not the weakest, this one's the weakest, but this one here is quite weak. So according to the situation, you would expect this one here to be the strongest, but actually in theory it kind of is, but what we'll find in practice, it's actually insoluble. Because it's insoluble, it can't act as a base, because it can't react with the acid. Only soluble things can react with acids. So it's insoluble, so it doesn't react. So if I was to compare, let's say, these structures here, let's have I write a list, and you were to ask me to put these in order of strength. This might be something that you have to do in an exam. Then ethylamine would be the strongest, number 1. Then it'll be ammonia, and then it will be phenylamine. Let's explain why that is. So ethylamine is a primary amine. So we've got a positive inductive effect here, which makes that lone pair of electrons more readily available to that H+. So it's quite a strong base, that one. And that's followed by ammonia. And the weakest out of those 3 is phenylamine, which is this one, because that lone pair of electrons there on that nitrogen is not readily available at all. It's now part of that delocalized ring system because of that phenyl group there. Okay, dead short again, just quarter of an hour or so, that little topic there. So we looked at basically the general properties of amines, so a bit how we turn phenylamine, which is essentially a base, or ethylamine, which is a base, into a soluble ionic compound by reacting with an acid, and how we take that soluble ionic compound and react with the base to make our amine again, and then we used smell to trace that reaction, and then we looked at base strength. Dead quick.